We are here in week 12. We're going to start chapter 11 this week as our kind of second part to the week here. So we're going to go ahead and start today with section 11.1. So really we want to introduce this chapter though because we're going to start looking at something that's kind of wildly different than things that we've been seeing up until now. So our new calculus concept for this chapter is the concept of a sequence and a series, which are very closely related. As is the broad theme of calculus, this is going to help us explore new concepts associated with infinity and how they can be of practical use to us. So what we really want to kind of do right now is go on down the line and say, like, what have we been doing with calculus? And what are we now going to be able to do with calculus if we now know about sequence series? How does this kind of relate to the stuff that we've already seen before? So here's our current calculus lineup. The first thing everybody does in Calc 1 is they talk limits. In limits, we ask what happens when we let a number get infinitely large? What happens when we let a number get infinitely close to, but not equal to another number? We've got those obvious infinities sitting right there, looking at us there with the limits, getting infinitely close to something and going infinitely far away from something. Made sense of those. Once we had those ideas of limits, then we were able to compute derivatives, which have just a ton of very practical applications, understanding the rate of change of any function. And when we're looking at the rate of change of a curve, we want to be measuring a change in output over an infinitely small change in input. That's our change in y. That's our dx term, right? That's our infinitely small change in input. We want to know what output change is that going to cause? That's our derivative at a point. Then we kind of upgraded from derivatives to integrals. As we've seen this semester, there is just a huge number of applications associated with integration. The act of adding together an infinite number of infinitely small objects. What we've seen, especially in our area and volume cases here, is that we can add up an infinite number of infinitely small n-dimensional objects and get an n plus one dimensional object, right? We added up all of our one-dimensional Riemann sticks and we got a two-dimensional Riemann area. Then also, I think it was in chapter 6, we added up a bunch of two-dimensional Riemann sheets, and we accrued enough sheets to get some volume, a two-dimensional area. An infinite number of those, infinitely close together, gave us a three-dimensional object. But it should very much be noted that integration did not go as well as derivatives did. Integrals are hard. There's a ton of cases where it's impossible. But the good news for us is that an integral, because it really represents the sum of an infinite number of infinitely small objects, is going to sort of be a special case of what we're going to define to be a series in this chapter. And so our study of sequences and series will, among other things, help us work out some of our integration issues. One of the highlights of this chapter is that the integral that I've shouted at you about a dozen times now, our e to the negative x squared, that we can't handle. We're going to find a roundabout way to actually perform that integration exactly rather than just looking at approximations with some sequence techniques at the very end of this chapter. So that'll be probably one of our last things that we get to in this class here, but a nice like culminating thing that we keep on seeing this one issue we run up against, and our study of sequences and series is going to help us kind of resolve that issue there. So one of the things that we're going to get out of sequences and series is we're going to get a little bit of help with some integration at the end of this chapter here. So, very importantly, this right now looks like the three things that you think of when you think of calculus, and we're sort of adding on a fourth item onto the list now, sequences and series. In this chapter, and by the way, notice I've been trying to intentionally kind of, italicize the word infinity in all of its versions that are here. And we're going to keep doing that with sequences and series. In this chapter, we're going to ask, what happens if we generate an infinitely long list of numbers? That's a sequence. And then the second part of this will be, what happens if you add up the infinite number of terms that are in a sequence? That's what we'll call a series. So a sequence and a series are super closely related. A sequence is a list, a sequence is a list. A series is the sum of the terms that are in the list. So very closely related. A series is a sum, a sequence is a list. Very closely related to each other. So we're hitting section 11.1 today. We're just going to talk about sequences. On Monday of next week, we'll talk series in 11.2. So a sequence is a list of numbers, and the list, very importantly, is in definite order. It is an ordered list. It's not just a collection, a set. It is a list, meaning it has order. We will only be discussing infinite sequences, but we will look at a very special application of some finite sequences in a video that I'll also make today. Our typical notation for sequences is to use braces to indicate that we're talking about a collection of objects here. So those curly braces are important. That's not a parenthesis. That's not a bracket. And that's a kind of notational thing that kind of matters to us here. So make sure you're using those braces whenever we're surrounding a terms in a sequence here. So we can describe a sub n as being the nth term of the sequence that's named a. We're holding it in braces to make sure that we understand that it's the entire sequence and not just the nth term. It's typically considered the default for any sequence is that we'll start with the first term and go infinitely far, but it's certainly the case that we might want to describe a subset of a sequence, a subsequence, where we maybe want to look at the 4th through the 15th term, and in that case we could give our lower bound of n equals 4, an upper bound of 15, and that would indicate to us just that finite subsequence. So typically these things are left off. If it's left off, it's assumed that it's from 1 to infinity, meaning all of the possible terms, from the first term out going infinitely far. It's pretty common to only actually indicate those lower and upper bounds if they are not 1 and infinity out there. So our standard here, these two are the same as each other because it is implied that we're starting at the first term and going infinitely far when we don't indicate any of those other parts right there. And in general, this is our list. This is how we can notate our list, just a comma separated list. It's the first term in the sequence, the second term, the third term, the nth term in the sequence, but it keeps on going. Remember, any sequence is technically an infinite sequence unless you specifically say that it's not, and therefore that dot 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 at the end is indicating, and this pattern will continue forever. Very importantly, notice that it only makes sense to ask what is the nth term in a sequence, but not what is, for example, the 2.3 term in a sequence, right? This a sub n sequence is a sequence that is sort of like a mapping with the integers being the domain. We can only ask what's the first, the second, the third. I can't look for like a term that's in between those two right there, right? So and I want to kind of just throw out right now, since we're seeing some gentle new notation on the screen right now, there's going to be a lot of new math notation that we're going to see in this chapter. This is kind of, in a sense, maybe a time where you start to grow a little bit in your ability to communicate mathematically the way other mathematicians communicate. We're going to see a lot of new notation here. I could write some more things out in words. I'm choosing not to because it's important that you guys learn to, a little bit more syntax for communicating mathematical ideas. So what I'm trying to kind of express to you right here is that when we think of a sequence that I'm naming A, what it's going to do is it's going to take the number n, like me saying, hey, what's the 8th term in the sequence? And you're going to say, oh, it's A sub 8. A sub 8 is the 8th term in the sequence A. And notice that in this case, that is taking an element of the integers, z, and it's going to return to us really any possible number that might be out there, any real number. But the very important thing is that the domain of a sequence function is always the integers. We're always going to be only plugging in positive integers into these guys here. This is compared to a general function f that we've normally, every f of x that you've ever seen in your mathematical career so far takes in some number x and spits out some number f of x. So this says f is a map that takes you from x to f of x, whatever that f of x function is. And in most cases that you've experienced in your life, and it's certainly not true that it's all cases, but generally, if nobody tells me some restriction on some function, I'm assuming that it can take in any real number and spit out any real number. Aside, of course, from some algebraic restrictions, for example, a square root function, I generally assume that I know that it's got to be the positive reals, stuff like that. Or if I'm talking about the 1 over x function, I know that it discludes 0. So aside from some algebraic restrictions, I typically think of all functions as taking me from the reals to the reals, or at least some subset of the reals that's going on out there. So our distinction here is when we think about sequences, we're always looking at an integer input, meaning we're always looking at the first, second, third, fourth term, right? We never talk about intermediary things in there. It's an integer count of which term we're considering. So as our first example here, let's go ahead and look at a kind of tough sequence right here and see if we can describe what mapping we're looking for. What is the operation that we would be performing to determine that number term in the sequence here? So here I've produced a sequence, and what we want to do is decide if we can come up with a function that would take in the number term in the sequence we're at and spit out that actual value right here. So I might kind of say these are the values in the sequence, and my index in my sequence, these are my n values. This is the first term, the second term, third, fourth, fifth, sixth. And so what I'm trying to do here is trying to kind of deduce what function this must be that we're having described to us here. And so this is just an eyeball game. This is just can you recognize some math terms and see where they come from? The first thing that's jumping out at me right here is I'm seeing a bunch of terms that look like cube terms here in the denominator. I recognize 64, 125, 216, 343 as the cubes of numbers that I know. I guess what I'm seeing here is this looks to me like I know that this is 4 cubed. I know that this is 5 cubed. This looks like 6 cubed. This looks like 7 cubed. So I feel like I have an idea of what's going on in our denominators down here. My next question might be what's up with the positives and negatives, and what's up with the numerator up here? So another thing that I'm seeing is my numerators. These don't look like numbers that I recognize as immediately as like 64, 125, 216, 343. I recognize those as cubes of numbers. I don't really 3, 8, 15, 24, 35. I guess a thing that I'm seeing here is that 3 is really close to 4, which is a square. 8's close to 9, which is a square. 15 is close to 16, that's a square. 24 is close to 25, that's a square. 35 is close to 36, which is a square. It looks like all these numbers are one less than the square of some other number. So it looks to me like this is like 2 squared minus 1, 3 squared minus 1, 4 squared minus 1, 5 squared minus 1, and 6 squared minus 1. Now, my last issue with this is we've got to decide what's up with these positives and negatives right here. By the way, notice that that 0 out front has been very unhelpful to us. I've sort of ignored it down here. But it does look to me like I can kind of decide that there should be some, and maybe I'll just bring in another color right here. Oh, that was a mistake. Is this going to be different? It looks like this is, oh, that's weird. Positive, negative, positive, negative, positive. So one thing we're going to have to come up with is what piece could we include in our function that's going to make this stuff change sign back and forth like that. So it feels to me like I have this idea so far that at the second term, we should be looking at 2 squared minus 1 over 4 cubed. And notice here, another nice relationship that I feel like I have here is 2 and 4 are pairs, 3 and 5, 4 and 6, 5 and 7, 6 and 8. These are all 2 apart from each other. So it feels to me like we should be looking at something like n squared minus 1 over, and it looks like the denominator term cubed is always 2 bigger than that n value that we were seeing. So maybe like an n plus 2 cubed. All right, this looks like my general descriptor of each of these terms in the sequence here. But again, I have this little issue of what's up with these pluses and minuses out here, man. That little like pencil thing did not work for me right there. These are pluses and minuses. So I need a term that's just going to be a positive or a negative, and it's going to switch whenever we have different power or different indexes here. So I'm noticing that when I'm at my second term, I want positive things. And in fact, for all even powered terms, I want positives. For all odd powered terms, I want negatives. So it feels to me like I could just introduce a multiplication by -1, but maybe place a power of n on it so that when n is an even number, when we're looking at our even terms like 2, that would be -1 squared, which is +1, which will leave all this stuff positive. Anytime that we're looking at one of our odd powered terms, we'll get terms like -1 to the 5th, and that will give me -1, and that'll introduce that negative power that's sitting out right there. So I think that I've come up with this a sub n function. I think that I could write this as -1 to the n times n squared minus 1, all divided by n plus 2 cubed. Now I have a generating function that could give me any of the terms that are in the sequence. So I kind of like to think this is, maybe this game is sort of like, could you tell me the 18th term in the sequence right here? And if you could, it's probably because you've identified the pattern that's associated with this. So I really do kind of like to play these games a little bit right here. Like, can you just recognize some stuff and build a function that would represent the terms that are associated with this? And really, this is definitely an eyeball it kind of thing right here. See if you can recognize some values that you might know. But in any event, we've come up for this example with the actual description of any nth term in the sequence. So maybe just say that before we move on here. Nth term in sequence. That's a sub n, and we've come up with a formula now. This formula matches all the rest. Ooh, and by the way, I should say, we ignored 0 that whole time. We should check and make sure that that works. Notice that if we're at index 1, if we're at the first thing in our list right there, then when I do plug in 1, I get -1 to the 1, so that'll be a -1. But I'm going to get 1 squared, which is 1, minus 1, which is 0. So I am getting 0 as my overall numerator. In the denominator, I'm going to get, what, 27 down there? 1 plus 2 is 3 cubed. So 0 over 27 is what I got from plugging in 1. So since we sort of ignored 0 in our construction before, it was good for me to go back and double check that guy right there to make sure that we weren't crazy right there. So I think that I've determined a good formula for our sequence right there. Again, it just takes a little bit of eyeballing, rewriting things in terms of some simpler functions that you can actually represent and understand for yourself right there. So if a sequence can be written as a function, like we just did right here, as in the previous example, then we can define the limit of a sequence the same as we define the limit of a function. So if I'm looking at this guy right here, if I say that a sub n is the sequence n over n plus 1, I can think about what the terms are going to look like in this guy. The first term in the sequence should be 1 over 2, because if n is 1, we're going to get out 1/2. If n is 2, I'm going to get out 2/3. If n is 3, I'm going to get 3/4, 4/5, 5/6. And what we're asking to ourselves is, what is this sequence tending towards? What value are we going to get if we let n tend off towards infinity? Well, it turns out that the answer to this guy is going to be the exact same as what we've originally looked at with limits, like back in the beginning of Calc 1 out there. When we originally looked at limits, we were given functions rather than the very related idea of a sequence, and we took the limit of those functions. We said, what happens if x gets infinitely large here? And that's when we often did kind of dumb things, like just go to our calculator and type in, let x be a billion is usually my my weak way of letting a limit tend off towards infinity right there. Hopefully what we can see is that these x terms, since they are the leading terms, they have the highest order terms in both the numerator and denominator, are both going to dominate this plus 1. This plus 1 is not really going to do anything for me once these x's get infinitely large. So therefore, we should see, if you kind of think about just ignoring the plus 1, this is just x over x. This certainly should be going to 1. I think our formal idea for this one was that we would factor out the x. We would do our limit as x goes to infinity, and we would factor out the x and get a 1, and then down here factor out the x and get a 1 plus 1 over x. We would let these x's cancel away together, and then when we take this limit, then that's where we get 1 over 1, which is equal to 1 right there. We can see that we're going to get the same type of action with our sequence out here, right? We can see that every single term that I create next in the sequence is a little bit closer to 1 than the previous term. These numbers are always increasing, but there's no way for us to get a numerator that's bigger than our denominator, since our numerator is always one more, or sorry, our denominator is always one more than the numerator right here. So it feels pretty, I feel pretty confident in making my statement that both of these limit statements are equal to 1. So the good news, so there's good news and bad news here. The good news is, if we can write a sequence as a function like this, the function n over n plus 1, then the limit of our sequence, the infinite limit of our sequence, is equal to the infinite limit of the associated function that it's related to right there. If we can do that, and that's the big key to this one. If we can write the sequence as a function, then their limits are equal to each other, and everything you need to know about sequences, you just need to know about our limit laws associated with functions. If the infinite limit of a sequence does exist and it's equal to some number L, then we say that the then we say that the sequence converges. Mixing up my words here. Then it converges. If the sequence does not converge for any reason, then we say it diverges. Just like we know with limits, there's several reasons why a limit could not exist. When we're talking, when we know about limits of functions rather than limits of sequences, we say that limits don't exist for several reasons, right? There could be a limit that doesn't exist because it diverged off to infinity. There could be a limit that doesn't exist. For example, the limit as x goes to infinity of sine of x. We know that that just oscillates back and forth forever. It never settles down to some value. So that doesn't converge because of oscillation, right? The important thing here is we're saying that every single sequence, the limit of every single sequence, either converges or diverges, 100% of them. It either converges to a number, L, or we say it diverges. So there's lots of ways that we could diverge. There's different ways to diverge. We tend off to positive infinity to negative infinity. We oscillate back and forth. There's lots of different ways to diverge. All of those, we say it diverges. So that kind of collectively holds a couple cases for us there, that label of divergent. So conveniently, we have that any sequence that can be represented as a function will share the same limit as the function, allowing us to use techniques associated with limits of functions to evaluate limits of sequences, right? So limits of functions, that was Calc 1. Limits of sequences, we're going to ultimately just say is going to basically be the same thing as long as we can make this relation. So this box right here is sort of the key. If we can write our sequence a sub n as a function f of n, then it will be the case that any limit associated with the function, any convergent limit associated with the function, is equivalent to any limit that's associated with the sequence. Very importantly, both of these capital L's are the same number right there. Right? So if the limit as x goes to infinity of f of x equals L, and that function f of n can be written as a sequence representation a sub n, then it will also be true that the sequence a sub n has a limit as n goes to infinity of that same value L. So this is just saying if we can write these two things the same way, if we can write a sequence the same way as we describe a function, then their limits are going to match. And that says to us we don't really need to learn anything new then to handle sequences. We just need to rehash our old limit information that we already know of out there. So let's look at an example of this. Given a sub n equals is the sequence defined by, in the nth term of the sequence, we'll get the natural log of n divided by n. What we want to know is what is the limit as n goes to infinity of a sub n here. So we are looking at we want this limit right here. And here's our unfortunate thing. Since this is a sequence, we don't necessarily get nice things like L'Hopital's rule that we might want in this case right here. But what our previous theorem just told us is we can treat this like the function, right? So our previous theorem says we can treat this as the function equivalent, right? So what that says to me here is that the limit as n goes to infinity of the sequence, natural log of n over n, should be equal to the limit as x goes to infinity of the natural log of x over x. So the letter change from n to x is trivial here. That's just a notational thing that we very often use n to indicate the index of a sequence, and we very often use x to indicate the independent variable of a function. That's just a naming convention. The more important thing that happened here is we dropped the curly braces indicating a sequence discussion to then have only a function discussion. Now that we're in function land, now it's appropriate for us to do things like use L'Hopital's rule. So now I'm going to say here equals by L'Hopital's rule right there, LH. This should be equal to the limit as x goes to infinity of 1 over x over 1, which is just the limit as x goes to infinity of 1 over x, and that's going to be 0. So we're seeing here this guy is converging, so we're expecting that this should also be, therefore, the same limit for our sequence as well. So not a super exciting example here, but this is again trying to just emphasize if it's possible for us to write a sequence to look like a function, then it's going to have all the properties that limits of functions have. Unfortunately, relating sequences to an equivalent function to help in taking limits won't always work. There's tons of sequences that are highly valuable to us that we can't describe by a single closed form function. By the way, I am going to make an additional video here associated with this stuff that's going to look at a super duper interesting sequence. I'm going to describe to you why it's very interesting and then do a little bit of the initial exploration of that sequence in that video. That'll be sort of like a little like bonus topic for our week here. So I'm going to come back and kind of hit like the most interesting special case of this. But the point here is, since we can't always rely on being able to describe a sequence equivalently as a function, we're going to need a better definition of convergence. We can't rely on describing this as convergence in the sense of a function's limit converging as well. So we need a little bit better of a definition here, and here's where I'm going to club you over the head with some new math notation. Fortunately for you, I've written out in a paragraph below it what I actually mean when I say this, but we really, really, really do want to get on board with a lot of this new notation here. So let's talk through this epic line right here. A sequence, a sub n, converges to the number L as n goes to infinity if, all right, so that first line, I expect you to all be on board with this statement right here. A sequence converges to a number L as the number of terms in the sequence goes off to infinity, right? N is the index, and we're at the nth term in the sequence. So as you go further and further out in the sequence, we expect it to converge on the number L if we go infinitely far out there, if the following statement is true. And actually, I'm going to go one better on you right here. All right, so here's really my statement in the mathiest notation I can possibly make here. And the very important ones that you need to know here is upside down capital A is for all. Backwards capital E is there exists. And because this is just a phrase that's used so freaking often in proofs, ST is a pretty common abbreviation for such that, just because that English two-word phrase comes up constantly in lots of math proofs. So these are really our three big notational things. And I guess there is one more in there that we don't necessarily haven't necessarily seen before. Is an element of. All right, so let's talk through what we see here. This is a tough line right here, but we're going to get through it. The idea here isn't too bad. We're going to look at a graph that's going to show us what idea we're seeing in this line right here. So if for all, or for every, if for every epsilon that is greater than 0, so epsilon's just going to be some number. Epsilon you should think of as like a margin of error. I'll kind of show you that in our graph here in a minute, but it's just a number. It's often a small number. It's just saying here it just needs to be a positive number. If every epsilon that's greater than 0, for every epsilon that's greater than 0, there exists some number n, capital N. Capital N is an element of the integers. So when I say n element of z, n-e-z, this is just saying there exists a number n that is an integer. There exists a number, capital N, that is an element of the set of the integers right there. So if for every epsilon greater than 0, there exists a capital N that's an element of the integers such that the absolute value of a sub n minus L, the value of convergence, is less than epsilon for every index beyond the index selected as capital N right there. So what this is saying to us then, if I'm reading this in English here, if for every epsilon greater than 0, there exists a value n, which is an integer, such that the distance, remember that absolute value is measuring distance, such that the distance from the nth term in our sequence to the convergent point L is less than epsilon for every value of n beyond the chosen value of n. So this is still really hard even if you're just reading it in English. So I'm going to try to explain this once before we go hit our example where we'll really see this thing. But it's good to not be wildly confused before we see our first example. So what this is saying to me is this. Think of epsilon as being a margin of error. Epsilon is going to be the distance away. Epsilon is the distance away our nth term in the sequence is from the convergent point, right? So if we're converging to 7, and if at the 8th value in the sequence we are at 7.5, then our margin of error would be 0.5 right there. That's how far away. What we're saying here is for any possible margin of error at all, we should be able to find a number n such that if you go out into the sequence at least as far as that number n, it's guaranteed that all values in the sequence beyond that point are going to have a distance from the convergent point L that's less than that margin of error that we want. So this is me saying, listen, man, I want to go out far enough in the sequence to get within 0.1 of the convergent point. How far out do I have to go? And you are going to do some calculation, and you're going to determine for me, if you go out to this capital N location out here, all values in the sequence beyond that will be within that margin of error that you wanted. And what's important is that we have to be able to do this for literally any margin of error that there could ever be. Big ones, or way more importantly, tiny ones. I need to be able to say, listen, I want to be guaranteed that I am within 1/billionth of the convergence value L. How far out do I need to go to always be within that margin of error? capital N is how far out we need to go. We want to be able to say for all indices bigger than capital N, you are guaranteed within your desired margin of error. What that sort of means to me is I can keep on making my margin of error smaller and smaller and keep being guaranteed that there will be a point in my sequence that I'm always guaranteed within that, no matter how much further out we go. Therefore, you should think we can continue to make our desired margin of error infinitely small, and there should always be a tail part of our sequence where we are stuck within that infinitely narrow margin of error, essentially meaning we have converged to that limit value right there if there's an infinitely small margin of error, right? So difficult to read this if you haven't read a bunch of math notation stuff, but I don't think the concept is too crazy. Our concept of convergence says if you go far enough out in the sequence, you will eventually be close to that point of convergence value. This is just making a statement that we need to be able to do that for any margin of error. There should be some point in the sequence where we're guaranteed within it. That is our equivalent definition of convergence here associated with sequences. All right. So all four of these notational things right here, you should expect to see these come up a lot. I'm going to use these at will for the rest of the semester. For all, for every, right? For all or forever. I feel like I think of this as for all. That's why it's an A. The notation for this is for all, backslash for all in math notation. I always often verbalize that as for every, but whatever. That's the same thing. So for all, for every. Cap backwards E, there exists. So A is with all, E is with exists, ST is such that, E is standing for element here. It is an element of the set. And you should think that's more like, I don't know, I guess this feels to me like a capital E is rounded, so it feels to me like a lowercase e. And that's because it's just one element of the set. Whatever. You'll remember these, I'm certain of it. So let's look at an example here. Let's use this epsilon definition of convergence to prove that this sequence here converges to zero. The way that we'll do that is by finding how far out in the sequence do we need to go to be within any given margin of error. If I can find a formula for n in terms of epsilon, then that's great for me, because then you could say to me, hey, Tony, I want my margin of error to be 1/1 billionth. And then I can immediately pop back to you and say, oh, cool, just go out to the 247,000th term in the sequence, and all the ones beyond that will be within your desired margin of error. That would be a guarantee to me that this function does, in fact, converge on the value 0. So let's go ahead and see if we can do a little bit of algebra to kind of make this guy happen. What we want to show, we want to prove the limit as n goes to infinity of a sub n is equal to 0. And what we just saw in this theorem that's stated right here is that what we really need to show is this statement right here, that for every epsilon there exists an n such that a sub n minus the point of convergence is within that boundary epsilon all the time. So what I'm thinking to myself here, so to find n in terms of epsilon, we want to know the distance that the nth term is from L, from our convergence point, is within the desired margin of error, is less than L. So the good news for us is that I know a sub n, it's this sequence right here. I know L, it's 0. So it looks like this is just going to turn into here the absolute value of 1 over root n cosine pi n minus 0 is less than epsilon. So let's do a little bit of algebra here and see if we can kind of convince ourselves of some more things associated with this. So one, that minus 0 obviously doesn't matter for us, so I'm just going to write this once ignoring it. And here's kind of the thing that I'm thinking. I don't really know what to do with this. In a sense, I kind of want to solve for n, and here's what I'm sort of seeing. I know that the cosine function can be positive or negative. That's a reason why I sort of need my absolute value bars right here. But what I also know about cosine as a function is that it's guaranteed to be between -1 and +1. So what that says to me is that a cosine function inside of an absolute value, its most extreme size is just 1. Any other value is going to be smaller than 1, right? So I'm worried about making my 1 over root n cosine pi n be small enough so that it's smaller than our margin of error epsilon. So I'm thinking to myself, our worst case scenario right now is that our cosine of pi n is 1. That's the biggest it could ever be. Anything else is smaller. It's going to help us get within our margin of error. So I'm thinking to myself, I really just need to guarantee then that 1 over root n is less than epsilon, because that's going to provide for me, even in my worst case scenario where cosine of pi n takes on the value of 1, then that's just equivalent to this. In all other cases, this would actually be, if cosine of pi n was anything other than positive 1, then this whole quantity would in fact be smaller. So I'm in a sense kind of guaranteeing that even my most extreme case is going to leave me being still less than epsilon. This is the biggest value. Let me just say over here, 1 over root n is the biggest possible value of 1 over root n cosine of pi n. Right? That's the biggest it could ever be when cosine has the value of 1 right there. So in that case, if I could just guarantee that 1 over root n is less than epsilon, then I know that I'm good to go, because this is guaranteed to be the biggest that our original sequence could have ever been. The other thing that's nice for me here is that 1 over root n is guaranteed to always be positive, so I think I can go ahead and drop my absolute value bars here. And what's good is that I can now solve for what n is required for what epsilon here. So I'm now going to just do a little bit of algebra right here. It looks like 1 over epsilon should be less than root n. I don't have any positives or negatives, so I don't have to worry about the sign changing here. And so I'm going to square both sides and say that our n value needs to be bigger than 1 over epsilon squared. All right. So this looks to me like my choice for capital N. My choice for capital N is, if I let capital N be at least 1 over epsilon squared, then I'm guaranteed to be within my desired margin of error of epsilon for all the terms beyond that in the sequence right there. Um, so this is sort of my answer to this question. If we choose our n to be anything bigger than 1 over epsilon squared, then we're guaranteed that all the values in the sequence beyond that n value are within the margin of error epsilon. All right. So what I'm going to go now do is I'm going to pop on over to Desmos right here. I've thrown the link in here so you can check this out for yourself. I've already brought it up on my browser over here, so let's go check this guy out. So I want to show you what I did here. What I did here is, first I graphed this function. I graphed the 1 over root n cosine pi n. I just made it a function instead. And you can see it here in red, right? This is our function here. You should see it looks like cosine, but very importantly, it has a decaying amplitude. And it makes sense that the amplitude is decaying, because we have an amplitude that gets smaller and smaller as our x value gets bigger and bigger, or our n value gets bigger and bigger. What I want to do is I'm going to define A to be our epsilon value, right? This is our margin of error. So what I'm saying here is, this is like my margin of error. I want to see that we are converging to within some desired margin of error. And if I make my margin of error smaller and smaller, I want to know that I'm within that guy, right? And so I'm noticing that early on in the sequence, the terms of the sequence are not necessarily within the margin of error. The function is outside of it. But then if I go far enough out, it seems like there should be some place where after that point, all of the terms in the sequence, or all of the values of the function, finally get to actually be trapped within that margin of error that I set up. And by the way, I'm not even sure if we've made it in yet. Is that okay? It looks like we're actually inside right now. So once I went out far enough, the entire function, and we're using the function as like our analog of a sequence here, fell within that margin of error, right? But we know that at the beginning that wasn't the case. So what I'm going to do now, our important thing, the thing that we just solved for, is we're saying to ourselves, listen, if we go out at least as far as 1 over that epsilon value, our margin of error squared, that's what we computed by hand a second ago, then that should guarantee for us that we're going to be within the margin of error at that point. So let me make this big. So here's what I'm seeing. If we are allowed to have a relatively large margin of error, then we can go out. And so what this red or pink is showing in the graph here is that if we go out beyond this one, beyond all the stuff that's in the red shaded region, notice, is within the margin of error. And notice that before the red region, we are not guaranteed within the margin of error. I can slide this guy out. I can make, and notice, by the way, again, my slider bar is not affecting the red stuff. My slider bar is affecting the green stuff. My slider bar is bounds on a y value right here. I'm then computing where the x bounds should be based on that, right? So as I make my margin of error, my desired margin of error gets smaller and smaller, that's going to move out how far out in the sequence we need to go before we're guaranteed within it. So now that I've made my margin of error, if I make my margin of error 0.4 right there, then we're not guaranteed within our margin of error early. But if we go out at least as far as, 6 point something, which by the way, we can't have a 6 point something. It looks like we need to go out at least as far as 7 in this case right here for a whole number. Then as far out as 7, we are guaranteed within that margin of error out there. And so this is kind of a nice thing that we can kind of zoom out. That we can kind of zoom out some more. I can let my margin of error get really, really small. And notice now that my margin of error is like 0.02, that's a really narrow green gap that we're trying to get within here, right? I can see that I'm not doing a great job at all. I guess I got to zoom way out if I want to find it out here, by the way. And I'm scrolling and I'm scrolling and I'm scrolling and I'm scrolling, and it looks like it's taken us a really long time. But what I do expect to eventually see, eventually, I think I've still actually got like a really long way to go right here. Shouldn't it be coming up at like in the 600s? Is that what I'm thinking? Um, no? Oh, it's telling me right here I need to go to 2500. I'm not even paying attention. Let's make our x-axis be here up to 25, 3000, I guess. Or rather, let's just do 2600 and let's have this be like 2500 or something like that. So the point being, it looks like this is now our cutoff, right? If we wanted that margin of error of 0.02, then we're seeing that if we're before 0.02, if we're before the line, oh man, here it is. If I zoom way, way, way in, then we would be able to see that this curve does in fact dip below. So we weren't guaranteed within the margin of error. See my red curve? It's actually outside of my margin of error bound out there. But as soon as we make it into that red graph region, we are guaranteed that everything beyond that is in fact going to be stuck within our desired margin of error there. So when we're talking about this epsilon definition of convergence here, we're saying for any epsilon I ever want, I want to be able to say to you, this is how close I need to be. You should be able to tell me how far out in the sequence we need to travel before all remaining terms in the sequence are guaranteed within that margin of error. If you can do that for any margin of error that there is, then you have proven that that function will converge on that proposed convergence value of L. So I kind of like this as a graphical representation. This graphical representation is sort of bad in that it's using a function, but it's very good in that it's kind of giving us this visual sense. And our slider bars are always helpful to us here. We really like to kind of see things change rather than just what things are. How do things change over time right there? So I think it's a valuable graph to play around with here. So let me pop back over to our place where we did stuff here. So we did a little bit of algebra over here to solve for how would we know. For any given epsilon, you now know how far out we need to go in the sequence right there. In that case, at least, we would be able to do that. I think this is going to move me, if I don't want that to happen. Let's do this. Just kind of separate. Oh, don't do that. No. Dang it. That was weird. Okay, all right, there we go. Separate those guys. So in this example, now in example 3, we're going to need to know this kind of stuff now. We want to determine whether this sequence converges or diverges right here. And let's sit here and stare at this for a second. This sequence 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. Notice what's happening in the sequence. This is not a sequence that it's possible to describe with any closed form function. There is not a function equivalent to this sequence. This is kind of an issue for us, right? So this is our a sub n right here. And very importantly, notice there is no function f of x that is equivalent to this a of n. Right. So our issue here is we can't use what we know about functions to help us out. I can't graph this thing. I can't use my function limit ideas here. We really need to know about our sequence limit convergence ideas here. So here's my idea with this guy. I am thinking to myself that it looks like this sequence only has zeros and ones in it. And it looks like every time we go a little bit further out in the sequence, it looks like we have 1 0, then 2 zeros in a row, then 3 zeros in a row, then 4 zeros in a row. So I can identify the pattern. I can like describe to you what sequence this is, but I can't like write it out as a function where you could plug in a number n and get out what value we're going to get at that location in the sequence, right? And so here's what I'm thinking. I think it wouldn't be unreasonable for us to believe, for example, that this sequence converges to like zero or something like that, because it seems like if we keep on going out further and further and further, we should get to an incredibly long list of zeros, right? So let's maybe say, so maybe this converges to zero. If so, I should be able to choose any epsilon greater than zero, and find the location in the sequence where all subsequent terms are within epsilon of zero. Right? So the question is, can I do this? So let's say, let epsilon be 1/2. Right? What I'm saying here is, suppose I want to find a margin of error of 1/2 from zero. What I'm then saying is, if this thing really did converge to zero, then it should be the case where I can go to some capital N, some location in this sequence, where all values beyond it are within 1/2 of zero. Notice that the number 1 is not within 1/2 of zero. So just by stating the counterexample of epsilon equals 1/2, this is saying to me that we should, if this thing truly converges to zero, which I think is our most sensible guess right here, then I should be able to choose any positive number epsilon and find a point in the sequence where beyond that, all of our values are within that distance from the proposed convergence value of zero. But if I choose epsilon to be 1/2, then I know that at any point in the sequence, if I am at any nth location in the sequence, then I know for a fact that there is another 1 coming up. Since 1 is not within 1/2 of zero, um, the sequence can't converge to zero. All right, so all I've really shown here is that the sequence does not converge to zero, but I'm quite confident then that this sequence diverges. Since I don't have any other idea of what this is I could make the identical argument for why this does not converge to 1 either. So let me just say here. So it looks to me like we are quite convinced that this is not going to be a convergent sequence here, since we can prove that it can't possibly converge to 1 or 0, and those are literally the only two numbers that are within the sequence. It's doing this oscillating back and forth. It's not spending equal time at each span of the oscillation, the min and the max, That doesn't matter. There's always going to be, at any point in the sequence, there's always a 1 after it. Therefore, there are margins of error that we will never be guaranteed to be within. Remember that our convergence definition says for all epsilon greater than 0. So it's very typical when you think of epsilon. Epsilon of 1/2 is outrageously large for a stand for. And when you think of epsilon, you should be thinking like 0.00001. Are we guaranteed to be able to go out to a point in the sequence where and when I say epsilon is like 0.0001, that's just like when I said earlier, like, oh, when I take limits to infinity, I usually just plug in a billion, right? That's my like stupid non-mathematical way to think about it, but it's also a really good way to just kind of like get your feet in the water right there and just say like, okay, like let's just call it this, right? But in general, epsilon is a very typical variable used in all of mathematics to represent an arbitrary, very small positive number. So that's what I'm thinking of here. So even 1/2 is, in my mind, a large value for epsilon, and anything less than 1 wouldn't work for us in this case. It has to be the case that for all epsilon greater than 0, we can find that n. Here I just found an infinite number of epsilons for which we cannot find a distance out in the sequence to be within our desired margin of error. Therefore, this is not a convergent sequence. Another important thing here is to notice that our convergence definition is based on the distance that A sub n is from L, regardless of the direction of the difference. So this is just saying to us for positives and negatives, as long as we're converging to 0 here, we can get this statement. If the limit of as n goes to infinity of the absolute value of the sequence is 0, then the original sequence itself converges. This is useful in some very small, not in some small examples right here, but this is very useful to be able to say, if you're stuck with a sequence that is doing some bouncing back and forth, it's okay for you to just take the absolute value of that sequence. Anything that you show about the absolute value of that sequence converging to 0 will hold for the original sequence to hold to 0. So I want to know the limit as n goes to infinity of -1 to the n over n. And so let's for a moment consider. So the weird thing about this one is it's going to be, and I mean, first thinking about this, the couple first terms in here, what are we going to get here, right? We're going to get, if n is 1, then I do get a negative, so I'm going to get a -1. If n is 2, we're even as a power, so this is going to be positive, and it's going to be a 2 down there, so a 1/2, a -1/3, a +1/4, a -1/5, right? I can look at those terms in the sequence there. So let's instead consider the limit as n goes to infinity of the absolute value of our sequence right here. So of our -1 to the n over n. Well, notice here that the absolute value is just going to, in a sense, say, don't worry about switching your positives and negatives here. So that's essentially just muting our numerator term right here, right? It's just always going to be +1. Therefore, this is the limit as n goes to infinity of just 1 over n. And we know about what happens here. If we let n get infinitely large, this is going to be 0. Therefore, the expression without the absolute value is also going to be equal to 0. That's what this theorem is saying for us right here. And notice all this is really saying is it was bumping back and forth, but we were eventually like honing in on 0. Even though it was above, below, above, below, above, below, we were honing in on 0 over time right there. And so this is just to say if the absolute value of a sequence tends to 0 as n goes to infinity, then the original one will as well. So we just discussed an epsilon statement about convergence, which said if a sequence converges to a number L, then for any desired margin of error from L, we should be able to go a specific number of terms, capital N, out in our sequence and be guaranteed to be within that margin of error. Can we make a related statement about divergence? We sort of can. We're gonna make an opposite statement right here about divergence. We're not going to play around too much with this one. I think our convergence idea is way more important here. But for divergence, we have sort of this opposite statement. So we're going to read through this very carefully again, nice and gross looking. To say that the limit as n goes to infinity of some sequence a sub n is equal to infinity, right? It's a divergence right there. It's a version of divergence. Not all divergences. We just diverge by oscillating up above right there. That wasn't a divergence off to infinity. Is to say that for every, and here it looks like we're picking some capital M number. For every capital M, some positive number, capital M, there should exist a capital N. That's an element of the positive integers, right? This is the same thing. It's saying there's some location out in the sequence that we can go, such that the value at that location in the sequence is going to be bigger than the number that we chose, as long as we've gone out at least as far as that. So what that's saying to me is things like this. If it's really true that our sequence diverges off to positive infinity, then I should be able to do something like pick a number. So I'm going to pick capital M to be like 1 billion, right? It's my limiting ideas right here. M is a billion. What I want to know is that there is guaranteed to exist some location in our sequence, the nth term in our sequence, the capital nth term in our sequence, such that all of the terms in our sequence, a sub n, right? A sub n, whenever n is greater than n. So this is all the terms in the sequence beyond that value of n are bigger than a billion, right? I picked m to be a billion. So this is like saying, hey man, how long does it take until we're guaranteed bigger than a billion? And you're going to go do some calculation. You're going to say, it appears that for all values, for all terms in the sequence beyond the 18th term, we're guaranteed to be above a billion. The very important point here is we would never test this for just one value of m, just stopping at a billion. What needs to be the case is that for literally every positive number that there is, you should be able to determine how far out in the sequence we need to go to be able to come up with something that's larger than that. So we can play the same sort of algebraic games here to prove divergence off to infinity as we just did in our previous example to prove convergence to zero right here. If for every capital M that could ever exist, literally every positive number that there is, if you can find how far out we need to go so that all the terms in the sequence are bigger than that, beyond that value in the sequence, then that's a guaranteed divergence off to infinity. And again, not just divergence. This is one of the ways that we can diverge, is the special case of diverging off to infinity right there. And also, certainly, we could just flip some inequalities and some statements here for negative infinity. But again, this is not talking to us about perhaps diverging by oscillation. Diverging to positive infinity is one of the ways that we diverge. This definition is only talking about that version of divergence right there. So again, don't be afraid of these gross statements right here. Try and get comfortable reading math. These ideas aren't really that crazy. Just throw some numbers in for yourself like I've been doing. A billion, a margin of error of 0.2, stuff like that. And I think it really helps to kind of see what these numbers are trying to describe to you here. So what else are we going to see? I'm not going to do an example with this. I care a lot more about proving convergence than proving divergence here. So let's look at some other cool ideas that we're going to see. I'm saying cool idea here somewhat sarcastically because I know that some of you are going to be like, oh crap, when you see this. So let's go ahead and take a look at example 5 right here. And let's prove something about the convergence of this difficult sequence right here. I want to prove that a sub n, being the sequence n factorial over n to the n, converges. That's what I want to prove. Okay, so let's go ahead and see if we can look at a couple terms here. Let's at least start with a couple. So our first term here is 1 factorial over 1 to the 1. That's just 1 over 1. That's 1. Second term in the sequence, 2 factorial over 2 to the 2. That's 2 times 1 over 2 times 2. That's going to be 2 over 4. That's going to be 1/2. What's a sub 3? 3 factorial over 3 cubed. That's going to be 3 times 2 times 1 over 3 times 3 times 3. That's going to be 6 over 27, which is, if I divide both by 3 there, I should have just canceled my 3's here. That's really 2 over 9. And let's do one more at least. And by the way, should really be doing this for sure all the time. Investigate your sequences. And by the way, I'm going to show you a cool place you can go, a really cool place you can go to play around with some sequences and to kind of check and see if something that you're looking at is maybe a known sequence. So here I'm seeing, so now what do we get? Now I got to really do some cancellation. 4's cancel. 2 is going to cancel with one of the 2's here, so I'm going to get 3 over 32. So a thing that I'm noticing here is it seems like this is continually a decreasing sequence, which by the way, that's one of our terms coming up in a minute here. It seems like this is going to keep on getting smaller and smaller. It also seems like a thing that I'm seeing is that it's always going to be a positive number over a positive number. And so I'm asking you, if a sequence is guaranteed to always decrease and it's always also guaranteed to be positive, then what do we think it's converging to? It seems like this is converging to 0. Right? So what we want to show is that the limit as n goes to infinity of this n factorial over n to the n is equal to 0. Right? So here's kind of the thing that I'm thinking. What we just showed over here is kind of two things, right? One thing I saw was that n factorial over n as a term in a sequence over n to the n, by the way, is greater than 0. I know that that's a true statement that I can make right here. The other thing that I'm seeing is that the nth term in the sequence a sub n is going to be equal to, that's n factorial over n to the n, which is going to be 1 times 2 times 3 times 4 times n, all divided by n times n times n times n times n. Right? So here's kind of the thing that I want to identify here. And by the way, this is a really important sort of tactic that's going to be coming up for us here. We've seen a little bit of this back in chapter 8. But now we're going to see a lot more of it here in chapter 11. One of the things that I'm seeing out of this fraction that I don't know how to deal with, and by the way, another thing that we could think to do for ourselves here, we want to take a limit, and it seems like this limit is going to be equal to infinity over infinity. So can we use L'Hopital's rule? Infinity over infinity says to me, L'Hopital's? But there is no derivative for n factorial. So that's going to be a problem for me, is that I don't have a general derivative for n factorial here. So I don't know, I can't use L'Hopital's rule because I can't take the derivative of the numerator term up there. So it seems like this is a place where we could just say, oh, this is equivalent to the function x factorial over x to the x. Take derivatives top and bottom. But I don't have a derivative for x factorial. So what are we going to do, right? So it seems like this could have been saved by L'Hopital's rule, but we got kind of stuck there with the lack of a derivative. So now that we don't have that, one of the things I always like to do is identify special terms in a sequence. And one of the things that's special to me, when I say special, I mean things I know something about. My problem is I don't know stuff about n factorial and n to the n, but I'm looking at when I write it out like this, I'm seeing that there is at least a piece of this that I am very, very comfortable with, which is the 1 over n part. So I'm going to think to myself, what if I wrote this as 1 over n times the remaining pieces? Right? And here's kind of the thing I'm seeing. What I'm trying to do is decide where this function lives, right? I want to know what size is it. And the thing that I'm seeing here is that this guy right here is always going to be less than 1 for any n greater than 1, right? As long as we have more than one term in our sequence, it's always going to be the case that that is contributing something that's smaller than 1. So therefore, what I know is that n factorial over n to the n is guaranteed to be less than 1 over n. And the reason that that's true is because by multiplying by all the rest of the terms, it's guaranteed to make us actually smaller, right? So I know that n factorial over n to the n is always going to be something that's less than just that first 1 over n term. The rest of that stuff is guaranteed to make it smaller because every term in the numerator here, why is that a 3? That's a 4, is guaranteed to be smaller than this one because we're going out to the nth term where this finally just caught to meeting up. So now let's go ahead and take these two ideas that we'd seen here, and let's combine them together. And I'm hoping that maybe you recognize the strategy that I am working towards right here. I now know two simple functions that are guaranteed to bound my complex function right here. And so it seems like I can now go ahead and take some limits. And what I'm finding here is that we're going to get 0 is less than our desired limit. Is less than 0. Oh, and by the way, I guess that these were equal to's right there. And these are equal to's. I don't know. It doesn't matter for the 0. It's less than or equal to 0, sure. Or it's greater than or equal to 0, sure. That doesn't really matter right there. And it's also the case that if there was only one term, then this would just be 1 over n. It would be equal to 1 over n right there. So I do think that these or equal to's are perfectly appropriate right there. And so notice that we're getting that this thing is stuck between 0 and 0. And so we can say, by our old friend, everybody's favorite thing in chapter 4 of Calc 1 is by the squeeze theorem, a sub n is going to converge to 0. It looks like we've squeezed it between two known parts. So I want to highlight to you why we care about the squeeze theorem now. The reason that we care about the squeeze theorem now is because what the squeeze theorem is always trying to do for us is it's always trying to put something we don't know about in between two things that we do know about. We saw in chapter 8 this thing called a comparison theorem, and we're going to see several things that are like that coming up here in chapter 11. They're going to be absolutely critical for us discussing convergence and divergence. We saw this with convergence and divergence of integrals, and we're seeing that integrals really are series. We're going to want to talk about the divergence and convergence of sequences and series. When they're really messy functions that we can't use our old techniques with, it helps to place them between two things that we do know and understand very well, like the number 0, like the function 1 over n. Since I was able to bound it between two known things, and those two known things had the same limit, and we were between it, ours must also tend towards that same limit, because we are, with it, this triple inequality is only true if this value here is directly equal to 0. Right? So using the squeeze theorem here is really like a comparison theorem type thing. It's saying find a lower bound, find an upper bound, find that the lower bound and upper bound converge, therefore it must be the case that the thing was in between, remained in between, as it will for all the n values out there. Right? So you should kind of notice that this sort of led us, in a sense, to a series of definitions right here. One of our really important things here when we explored this function was that it was a decreasing function that was bounded below, right? And in fact, bounded above as well. I know that this sequence right here has a upper bound of 1, has a lower bound of 0, and I know that it will always decrease. So let's kind of identify some of these definitions here. These definitions are easy, which is why I just made a big old list of them, and then we'll conclude one super important conclusion from these definitions. We say that a sequence is increasing if the n plus 1th term is bigger than the nth term for all of the n values that are out there. This says to me, I don't care where you are in the sequence, I want the next term to be bigger than the current term. If that's always true, that's just our definition of increasing. Conversely, for decreasing, the only thing I did was switch that to a less than sign. We want the next term to be less than the current term for all of our possible terms that are out there. Slightly differently, and the book skips these two, by the way, non-decreasing means it's either increasing or the same, right? If you ever get a sequence that like increases, but then literally just becomes flat and like stays 5 forever, it's no longer increasing if the sequence is like 5, 5, 5, 5, 5, but it's not decreasing, and so we call that a non-decreasing sequence. It's a little bit more important that we identify the increasing and decreasing, but I don't think these are too big of stretches of the imagination right there. You are not decreasing if you are staying the same or increasing. Staying the same or increasing. You are not increasing if you are staying the same or decreasing. And that's exactly the notation I've got in there. Monotonic then kind of wraps up some of the previous ones that we've seen. Monotonic says that it only has one trend. Mono is 1, and where is it tending towards? This is a monotonic sequence if it just increases or just decreases. So I would say that this sequence here is a monotonic sequence. It is a decreasing sequence. Any sequence that is either increasing or decreasing is monotonic. Monotonic is just covering both of them right there. Right. By the way, this is bothering me right here. Can I erase just that one part? Yes, thank you. Okay, back to this. Monotonic, right, is just that. Is it increasing or is it decreasing? That's all monotonic is covering. Another thing that we saw is that we would like to identify what's going on here. Oh, I see what I'm actually. Uh-oh. Now I'm getting myself. Okay, we're back to select. Okay. Is that we are bounded above if there exists a capital M such that all the terms in our sequence are less than that capital M. So here, capital M is our upper bound. And by the way, I think it's appropriate that I change this to a lowercase m right there. Very common to use lowercase m and capital M as a lower bound and an upper bound. So I'm saying here a sequence is bounded below if there exists any capital M at all. It doesn't have to be a special bound, it's just any bound at all, such that every single term in the sequence, such that a sub n is less than m, for all the terms in the sequence, for all the n values that are positive integers. We want to say that that term in the sequence is less than that bound. Importantly, notice here that we identified positive 1 as a smart capital M choice up here, but very importantly, notice that I could equally say that this sequence is bounded above by 57. I'm not wrong when I say that. 57 just doesn't happen to be the least upper bound. It is an upper bound, but it is not the least upper bound. Least upper bounds are extra valuable to us because we know that we couldn't have brought it any lower. 1 is certainly the least upper bound of this function because anything below 1 would disclude the first term in our sequence right there, so it wouldn't make it. So I think it's important to kind of note, and I should write this here. I don't understand why this switches back and forth like this. I just feel like I don't, it works sometimes. Anyway, for the above example, the value of m equals 57 is an upper bound. But we can see by inspection that m equals 1 is the least upper bound. All right, so just don't get lost there. When we say a bound, you don't necessarily have to have found the literal edge of where it's at. A bound is any number that's above all the rest of the numbers in the sequence. So again, 57 is an upper bound for that upper sequence. It's just not a super helpful one. 1, the least upper bound, is much more helpful to us in identifying where this thing lives. So bounded below, same statement. If there exists a lowercase m such that all the terms in the sequence are bigger than lowercase m, for all the terms in the sequence. This isn't like a go out far enough thing. This just says all the terms in the sequence are bounded above or below by this value. We say that a sequence is a bounded sequence if it is both bounded above and below. So notice real quickly, there's no such thing as a monotonic sequence that's both increasing or decreasing. You have to be one or the other or neither. Bounded is not like that. Bounded is saying both. If you are a bounded sequence, that means there is a guaranteed known upper and lower bound. They don't have to be the least upper bound and the greatest lower bound, but they are just known bounds. So I can say that the sequence defined by cosine of n is a bounded sequence because I know it has a greatest lower bound of -1, or sorry, has a least upper bound of 1 and a greatest lower bound of -1. I can identify the more special bounds associated with that. So suppose that a sequence is strictly increasing. I'm going to tell you it is bounded below by m equals 2. It is bounded above by capital M equals 7. What can we say about the sequence? This is a pretty important claim we want to be making here. And so I'm thinking to myself, this is sort of like my a sub n axis here. I guess that was a bad axis to start on right there. Since we know we're stuck between 2 and 7, I don't need that negative part down there. So I'm just going to say here, this is my a sub n axis, this is my n axis. So this is going to say, what's the first term, what's the second term, what's the third term, what's the fourth term. What I have been told is that m equals 2 and that capital M equals 7. So I know for a fact that my sequence will always live within these bounds right here. I know that my sequence is guaranteed to increase forever. What can we say about the sequence? The reason I'm asking this question this way is because I'm suspicious that some of you listening right now are going to overstate the answer to this. The overstated answer that's not correct here is that this sequence will converge to 7. The reason that that's not correct is because I don't know that capital M is my least upper bound. I just know it's an upper bound. So I'm thinking to myself, it might be the case that this sequence just increases and increases and increases, but maybe it's only converging to something like 4 or 5, right? It's not necessarily converging to 7. 7 is an upper bound. I don't know that it's starting at 2. 2 is a lower bound. But what I can say about this is if it's increasing forever, it's never going to change directions ever. If it's always going to get bigger and bigger and bigger, and it's guaranteed to be bounded above by 7, then either it's converging to 7, or if 7 isn't the greatest upper bound or the least upper bound, then it's going to converge to whatever that least upper bound is going to be. So let me say here we can say the sequence converges. We can't say it converges to 7. Since we don't know if 7 is the least upper bound. Right. So just kind of remember, when we say something's bounded by something, we're not necessarily saying it's the edge. We're just saying it's the bound. I think of the edge as like the least upper bound or the greatest lower bound. Those are special in a sense right there. So we can say that it converges. So our kind of conclusion from what we just looked at there is a very, very special theorem. It's called the monotonic bounded theorem. It's a super useful theorem for identifying if a certain sequence converges or not. This very simple theorem, out of all the terrible notation you've had to see today, is much more simply stated. If a sequence is both bounded and monotonic, it is guaranteed to converge. So what this says to us is if we can prove that a sequence is bounded, and then if we can prove that it's monotonic, then those two things together will combine to conclude it must have converged. What we don't get from this is we don't know what it converged to. This is not a statement that says, then it converged to L. All this is saying is, I promise it's going to converge if these two conditions are met right here. We might need to do a little bit of extra work to judge that, which we're going to do. Right? So the problem with this sequence, or with this theorem, is that it's fully dependent. Its use is fully dependent on us being able to prove two things, boundedness and monotonicity. Right? And we can't prove convergence using this theorem unless we can prove each of those separate things first. So it looks like what we need is some new proving techniques to help us out with one of these. And one of the most common proving techniques associated especially with all these integer mapping functions like sequences, whenever we're dealing with integer-based things like we've been all section today, is a proof by induction. So what I'm going to do right now is this. There's a couple things that are about to happen here. I think that proofs by induction are best shown kind of on their own. I don't want to just introduce this within an example about the monotonic bounded theorem because proofs by induction are kind of their own whole animal, but you need to know about these. This is just a really important math thing that happens out there, a proof by induction. So what I'm going to do right now is I'm going to cut this video right now. I'm going to just restart and I'm going to kind of wrap up my proof by induction stuff right now just so that this can be its own separated video right here. I'm going to first explore what's up with proofs by induction. Then we're going to come back and we're going to do an example of proving something using the monotonic bounded theorem. We're going to prove that a sequence is convergent. We're going to do it by proving that the sequence is bounded, proving that the sequence is monotonic. Both of those proofs are going to require their own proof by induction, and then we'll be able to conclude that it is a convergent sequence. Then we're going to say, now that we know it converges, can we do a little bit of extra work and show what it converges to? And we'll get that guy. Then I'm actually going to go ahead and I'm going to get real spicy this week and make a third video. And in the third video, I want to show you guys some extra cool stuff about one of probably the most famous sequence. Okay, depending on how you define famous, I'm going to make an argument to you that it could be said that this is the most famous sequence known in the world. It is a current open problem in math that is of extreme interest for mathematicians around the world to have a proof that this thing does converge in the way that we think that it does. And it's currently an open problem in math. It's something that I've explored quite a bit with some computer programming things, and it's just got some really cool ideas that are related to it. So I'm actually going to look at a third video there. And finally, what I'll also do in that third video is I'm going to show you guys a place that you can go to look up any sequence ever. And if you ever run across a sequence for the rest of your life, you can see if there's a ton of stuff known about the sequence that you didn't already know. And by the way, I'm kind of thinking to myself, just like this guy that we looked at, the very first one today, I think that we can just straight up look this guy up. And that's a weird thing to be able to look up. And so I want to show you this very special place on the internet where a bunch of people have been compiling a ton of sequence data. Oh, wait, it's for integer sequences only. Okay, that's okay. The one that we're going to look at, the special case that I'm going to look at in my like sort of bonus video this week is going to be an integer sequence. And so I'm still going to show you guys that stuff. This won't be lookupable because this is not an integer sequence right here. We have non-integer values in our sequence, but there is this super cool resource that I'll also show you guys out there. So where we're at right here is I'm about to cut it right now so that we can look at our proofs by induction and then prove that a sequence converges using the monotonic bounded theorem. That'll be a sort of like the finish up to this video. Probably take me like 30-ish minutes there. And then I'm going to show you guys sort of our special topic video will be an extra one that I'll create here. We're going to look at a very, very, very special sequence called the Collatz sequence. And look at why it's so special and how we can investigate it using some computer programming. So that's going to wrap it up for this part of this video. I still need to hit you guys with proofs by induction and an example associated with the monotonic bounded theorem. I'm going to make that guy right now. So we'll just have this a little bit broken up here this week. So I will see you momentarily for our proofs by induction here.